Traditional math algorithms require us to calculate from right to left, starting with the smallest units. But the brain naturally processes information, including numbers, from left to right. This is where place value decomposition helps. Instead of stacking digits, we break the numbers down into their actual values and calculate from left to right, keeping the actual scale of the numbers clear at every step. Take a basic addition problem like 64 plus 25. We separate the 25 into its structural components, 20 and 5. We calculate the largest value first, adding the 20 to the 64 to reach 84. Then the remaining 5 drops in to finish at 89. Starting with the largest values reduces cognitive load. You avoid the need to carry small numbers and immediately anchor your thinking to the correct scale of the answer. Subtraction introduces a specific friction point. The left-to-right process seems to stall when a digit in the top number is smaller than the one below it. Consider 123 minus 59. We solve this by expanding both numbers into their full place value forms and stacking them. 100, 20, and 3 sit directly above 50 and 9. Now we subtract straight down the columns. The 100 drops down. In the tens column, 20 minus 50 leaves a temporary negative 30. In the units, 3 minus 9 leaves a negative 6. Finally, we combine these intermediate figures horizontally. 100 minus 30 gives us 70, and 70 minus 6 resolves to a final answer of 64. Working with a temporary negative debt is mechanically simpler than traditional borrowing. It removes the need to cross out digits and manage cascading logic in your head. Two-digit multiplication has a common trap. It's easy to multiply the tens together and then the units together, while completely missing the cross products. Look at 13 times 27. This problem can be mathematically broken down into partial products to ensure nothing is missed. 13 times 27 is expanded into 10 plus 3 multiplied by 20 plus 7. This creates 4 specific steps: 10 times 20, 10 times 7, 3 times 20, and 3 times 7. To see why these 4 parts matter, we can use the array model. We draw a rectangle divided into lengths of 20 and 7, and widths of 10 and 3, creating 4 distinct quadrants. We calculate the area of each quadrant to get 200, 70, 60, and 21. When these 4 blocks merge, we see the total is 351. Try applying this area logic to 48 times 4. If we split the 48 into a 40 and an 8 and multiply both by 4, we get 160 and 32. Combined, they reach 192. Multiplication is the calculation of area. Ignoring cross products means physically leaving out large sections of the total shape. Division works differently. Strictly separating hundreds, tens, and units can sometimes make the calculation harder. Take 416 divided by 8. Attempting a rigid decomposition of 400 plus 10 plus 6 brings us to a stop. 400 divides evenly by 8, but 10 does not, halting the process. Instead, we look for friendly numbers. We group the remainder into 16, turning the equation into 400 plus 16. Now both parts divide cleanly by 8, giving us 50 and 2, a final answer of 52. Mental math is about molding and grouping numbers to fit the specific constraints of the operation, rather than following a rigid set of rules. These 3 approaches for place value decomposition provide a consistent framework for mental calculation. First, calculate left to right to establish the scale. Second, use temporary negatives to simplify subtraction. And third, use the area model to ensure you capture every part of a multiplication. Moving away from paper-based algorithms toward manually dissecting values replaces rote memorization with a direct understanding of how quantities interact.